The Limits to Einstein's Theories of Relativity by Francis T.S.U., Professor Emeritus, Penn State University. This talk is intended to demonstrate the difference between what I call the non-temporal universe proposed by modern physics and the temporal universe that I am proposing here. Before I get started, however, I would like to introduce two questions all scientists face over the course of their careers, followed by three generalizations regarding how both scientists and the general public view scientific work. Question number one. Should I, as a scientist, uncritically accept the presuppositions on which today's theories rest, especially when doing so will ensure me greater acceptance in the scientific world? Question number two. Should I pursue only that which will further my career, even if doing so may prevent me from discovering more fundamental truths? Generalization number one. Even the most independent thinkers will, over time, tend to become defensive of their own theories and consequently tend to overlook possible flaws in and exceptions to them. Generalization number two. Most people will defend orthodoxy, even in the face of incontrovertible evidence. Generalization number three. Mathematics tends to legitimize any particular theory in both the academic world and in the public mind, sometimes making the work seem more important, more serious, more true, and even more real than it really is. This slide shows some of the fundamental differences between science and mathematics. Quote, "Ontology is a prerequisite for physics, but not for mathematics. It means physics is ultimately concerned with descriptions of the real world, while mathematics is concerned with abstract patterns, even beyond the real world. Thus, physics statements are synthetic, while mathematical statements are analytic. Mathematics contains hypotheses, while physics contains theories. Mathematical statements have to be only logically true, while physics statements must match observed and experimental data. The distinction is clear-cut, but not always obvious." End quote. Saheed Veradi, Sahand University of Technology, Tabriz, Iran. Quote, "Mathematics, the science of structure, order, and relation that has evolved from elemental practices of counting, measuring, and describing the shapes of objects. It deals with logical reasoning and quantitative calculation, and its development has involved an increasing degree of idealization and abstraction of its subject matter." End quote. Craig C. Fraser, Encyclopedia Britannica. Because physics often relies on mathematics, one could go so far as to say that physics needs mathematics. The converse, however, is not necessarily true. Mathematics does not necessarily need physics. Simply because physics utilizes and often relies on mathematics does not mean that physics and mathematics are equivalent. Mathematics can be thought of as a tool, one, incidentally, that is often used in physics as well as in a host of other fields. In its most abstract forms, mathematics involves an increasing degree of idealization. As a result, and similar to language, certain forms of abstract mathematics do not have to correspond to physical reality. This is why certain mathematical principles may be no more a reflection of how the world actually works than particular principles, theories, or ideas in economics, philosophy, or political theory. Unlike in mathematics, every law, principle, theory, postulate, or paradox in the realm of physics must comply with physical reality. In other words, each must comply with the actual conditions of our universe, where the passage of time is unvaried and never stops and never goes backward. As a result, I am defining our universe as a temporal, i.e. time-space universe, where t is greater than 0. Any scientific law, principle, theory, postulate, or paradox that does not comply with physical reality cannot exist in a temporal universe. Einstein's special and general theories of relativity are no exception. our universe as a temporal, i.e. time-space universe, where t is greater than 0. Any scientific law, principle, theory, postulate, or paradox that does not comply with physical reality cannot exist in a temporal universe. Einstein's special and general theories of relativity are no exception. This slide shows that Einstein's special theory of relativity can be derived within an empty space paradigm by Pythagoras' theorem. C delta t prime squared equals c delta t squared plus v delta t prime squared, where t prime is the relativistic time dilation of the moving subspace with respect to a static subspace. Delta t is a section of time that has elapsed within a static subspace relative to the moving subspace. V is the velocity of a moving subspace. C is the velocity of light. And S represents the light source. Einstein's special theory of relativity can be written as delta t prime equals delta t over the square root of 1 minus v over c squared. Since delta t prime is greater than delta t, we can see that the moving subspace has a section of time gain relative to any static subspace. We also see that the special theory of relativity is relativistically directionally independent. Similarly, the special theory of relativity can be derived within a temporal, i.e. t greater than 0, space, as shown in this slide. If the derivation starts at time t equals t1 from light source S, then it will take time delta t, i.e. t equals t1 plus delta t, for the light particle 1 to reach position 1. Yet, delta t is a subsection of the space-time continuum for light particle 2. Thus, delta t is less than delta t prime, meaning that light particle 2 reaches position 2 after light particle 1 reaches position 1. In other words, since v delta t is a subdistance of v delta t prime, light particle 1 reaches position 1 before light particle 2 reaches position 2. It will take light particle 2 an additional time of delta t double prime to reach position 2. Because light particle 2 must travel an extra distance of c delta t double prime equals c delta t prime minus delta t to reach position 2, it must reach its destination sometime after light particle 1 reaches position 1. As I see it, the moving particle has no section of time gain relative to the static position 1, since time at position 1 and 2 are the same when moving particle reaches position 2. The time elapsed at position 1 is actually delta t prime equals delta t plus delta t double prime instead of delta t, as it would be according to the special theory of relativity. From the previous slide, we see that the time elapsed by the time particle 1 reaches position 1 is actually delta t prime equals delta t plus delta t double prime, instead of just delta t as assumed by the special theory of relativity. Given the above, under what conditions is a special theory of relativity legitimate within our temporal, i.e. t greater than 0, universe? Note that by raising this question, I am not discounting the value that Einstein's theory has in producing one of the most important equations in modern physics, I equals E equals mc squared. The special theory was derived under the assumption that mass is at rest and therefore not in motion. But from the standpoint of physical reality, mass cannot totally be at rest because it is a temporal, i.e. t greater than 0 substance, and therefore constantly changing with time. In this space-time diagram, the present moment is located in the middle, where t equals 0. This point corresponds to the roughly 14 billion light years that have elapsed since the Big Bang. The past time domain, i.e. t less than 0, corresponds to a certain past, or what I'm defining as virtual events. The future time domain, i.e. t greater than 0, on the other hand, corresponds to uncertain physical consequences. The present moment at t equals 0 continuously progresses to a new present moment according to the equation t equals 0 plus delta t prime. The present moment corresponds to an absolute certain moment. In view of this diagram, we see that it is impossible for a particle, no matter how small, to travel ahead or behind the pace of time-space within our universe, if it is to be part of our real and temporal universe rather than part of a fictional universe. This slide shows the paradox of time traveling. Einstein's special theory of relativity tells us we can experience a slowing down of time relative to someone if we are traveling faster than they are. But the rules of temporal universe shows us this is impossible. We cannot change time. We can only change with time. The diagram in this slide epitomizes the nature of a temporal space. We see that the universe is about 14 billion light years old. The present moment, i.e. t equals 0, divides the physical future from the virtual past. The negative time domain, where t is smaller than 0, represents past certainty. The positive time domain, where t is larger than 0, represents future uncertainty. When t is greater than 0, space changes with time, since time is a dependent forward variable. When t is less than 0, time changes with space, because in this case, time is an independent variable. In temporal reality, however, t is never less than 0. Space at t equals 0 is the only moment of absolute certainty. We cannot change time, and we cannot travel slower or faster than time's unvarying pace. Necessary conditions. The present moment where t equals 0 defines physical and virtual realities. Time must be greater than 0 if any solution is to be physically realizable, or in other words, based on reality rather than fiction. Anything considered real science should be physically realizable. If not, it should be considered pseudoscience. Science is not deterministic. In other words, science can only approximate reality with more or less accuracy and more or less precision, and from a greater or lesser number of perspectives. It can never fully determine reality. Since the general theory of relativity is based on a time-independent deterministic variable, it is a deterministic theory instead of a time-dependent non-deterministic theory. As a result, the general theory of relativity is not physically realizable within our temporal universe. Space curves with time, but space does not itself curve time. Note that practically all of classical science has used past deterministic certainties to analyze future outcomes. This is precisely why all scientific laws, principles, theories, and paradoxes are fixed and deterministic rather than changing naturally with time. And this includes some of the probabilistic distributions such as wave function, Boltzmann distribution, and many others that do not change with time. Once again, it is the present moment where t equals 0 that divides physical and virtual realities. Only in the present moment, where t equals 0, can we have absolute certainty in the material world. In other words, only the present moment corresponds to physical reality. In contrast, the past, where t is less than 0, corresponds to virtual and thus certain consequences, while the future, where t is greater than 0, corresponds to physical and thus uncertain consequences. In short, the universe and its subspaces only exist in the absolute material sense in the present moment when t equals 0. All past consequences are virtual in certain events, but with no physical substance or time dependency. All past consequences, therefore, constitute information. Similarly, all future consequences are physically realizable and change with time. In contrast to John Wheeler, who said, "Space-time tells matter how to move, matter tells space-time how to curve," I am proposing that time tells space how to curve, while space does not tell time how to curve. This slide shows how time curves a subspace. If we could reverse time, we might be able to say that space curves time. The problem is that we cannot reverse time. Unfortunately, the possibility of reversing time is precisely what the general theory of relativity is proposing when it treats time as an independent variable. In conclusion, the special theory of relativity does not apply to our temporal, i.e. t greater than 0, universe, because the theory presupposes the possibility of empty subspace. Since the general theory of relativity treats time as an independent variable, it is also not physically realizable within our temporal universe. Space curves with time, but the converse is not true. Space does not curve time. Related articles. What is wrong with theoretical physics today? The nature of temporal, i.e. t greater than 0, quantum theory, part 1 and part 2. The nature of relativity, coming soon. Thank you.